In this video, I'm going to prove that row rank of a matrix is equal to its column rank, and as a corollary, it follows that determinant is equal to 0 implies linear dependence of the rows and columns of the determinant, which is not the common theorem about determinants, which says that if the rows and columns are linearly dependent, then the determinant is equal to 0. This is the opposite, which is not a common proof and rather difficult to find, actually. I proved this in a previous video, but what I really needed was this corollary, which I didn't have at the time, so it wasn't quite that tight. This is a tight proof, starting from just a very basic assumption. Now, I note that interchanging rows and columns of a matrix array doesn't change the linear dependence. And the reason for that is the definition of addition and multiplication of vectors. As an ultra simple example, for example, if I have 2c1 plus c2 is equal to 0, that is true whether I have components 1, 2, 2, 4, or if I interchange these two rows, 2, 4 with 1, 2, then 2c1 plus c2 equals 0 still holds. Now, I note that every array or matrix has a largest subdeterminant. That's an elementary, obvious fact. For example, if this is an array, the double x's might be the largest subdeterminant of A, and it's also possible that another determinant of the same size, for example, the zeros here, might also be unequal to 0. But the point is that it has a largest subdeterminant unequal to 0, and any determinant larger than that will be equal to 0. Now, I'm going to prove the assertion by construction, and to do that, I'm going to take an example of an array which has the largest subdeterminant of size 2 unequal to 0, and all larger subdeterminants equal to 0. And I'm also going to assume that by interchanging rows and columns, I've put that largest subdeterminant in the upper left-hand corner, and that's the illustration that I have here, where this is D2, which is unequal to 0, and every determinant that I form from these elements of larger size than D2 will be equal to 0. And that's what enables me to now express rows 3 and 4 as a linear combination of the rows through the determinant unequal to 0, 1, and 2, and columns 3, 4, and 5 are linear combinations of the columns through D2 unequal to 0. And to show the procedure now, I'm going to begin by noting that if I expand this D3 about the third column, what I will get is A13 cofactor A13 plus A23 times the cofactor A23 plus A33 times the cofactor A33, which I can solve for A33 in terms of A13 and A23. That's the core principle of everything that happens. Now, if I replace this row, this column, with this column here, and repeat that calculation, I will get the same thing. A31 is the same linear combination of A21 and A11. If I place this column in this column, I will get that A32 is a linear combination of A22 and A12. Now, if I replace this column in this position, I will get that A34 is a linear combination of AT4 and A14, and the same for this column in that position. It gives A35 as a linear combination of the same linear combination of A25 and A15. All of what I've done here, I've actually taken the trouble to spell it out and write out all the equations. For example, this determinant with the A13, A23, A33 is here, and that's the third equation here. which shows that A33 is a linear combination of A13 and A23. Note that if you have all the equations spelled out, here you get the first column, here you get the second column, and here you get the third column, and these equations say that no, A11, A12, here you get, I'm sorry, here you get the first row, the second row, and the third row, and those equations in sum say that R3 is A13 prime over A33 R1 plus A23 prime over A33 R2. And so that's the procedure to get row 3 as a linear combination of 1 and 2. And I can repeat that whole procedure if I with the fourth row in the third row position to get that R4 is a linear combination of R1 and R2. And I can repeat that for any number of rows that I would happen to have here. Now to get columns, to get the column relationship, linear dependence of the columns on columns 1 and 2, I know to begin with that if I expand the third row here, if I expand the determinant about the third row here, then I get that A31 times cofactor A31 plus A32 times cofactor A32 plus A33 cofactor A33 is equal to 0, which lets me solve for A33 in terms of A31 and A32. Now, if I replace this row with the first row, then I have a determinant with 2 rows equal to 0, and I can write the same thing, and that gives me A11 cap A13 plus A12 cap A31 cap A32 plus A13 cap A33 equals 0. Gives me A13 is the same linear combination of A11 and A12. And I can similarly for this row here, gives A23 is a linear combination of A1, A22. Then I can replace this column with this column to get A14 is linear combination A11, A12, and so on. The fifth column, place it here. All of this, the important thing is to see the fact that setting the determinant equal to 0 by expansion in this column gives me row dependence. Setting the determinant equal to 0 by expansion of this row gives me column dependence. Now the procedure is spelled out over here, and if you don't understand what happened here, then this procedure doesn't make that much sense. But if you get the principle, then this will make sense. And here I've spelled out every step that I've described is spelled out here for row 3 in position 3 and for column 3 in position 3. Here are the equations, and for the column equations, you see that column 3 is a linear combination of column 1 and column 2, given here. Now, for determinant equal to 0 equal linear dependence, I note that a determinant is simply another array which happens to be perpendicular, and it will have a largest subdeterminant, and then I can express the rows and columns of that determinant in terms of the rows and columns through the subdeterminant, the largest subdeterminant, which is unequal to 0. Thank you.